Hello everyone. I'll discuss about the experimental law of Coulomb in this video. Coulomb's law is given for force between two point charges. What we mean by point charges? Point charges are charges whose size is very small compared to the distance of separation between the two. Coulomb's law states force between two such very small objects separated in a vacuum or free space where the distance of separation between them is very large compared to their size. And in that case, force between these two charges is directly proportional to magnitude of the charges and it's inversely proportional to square of the distance between the two. We can mathematically give the expression for force as K times Q1 Q2 by R square, where K is the proportionality constant and Q1 Q2 are the magnitudes of the charges, R is the distance of separation between the two. And this proportionality constant K value is equal to 9 into 10 power 9, or this can also be said in terms of permittivity as 1 by 4 pi epsilon naught, where epsilon naught is the permittivity of free space, which has a value of 8.854 into 10 power minus 12 farad per meter. This force can be given in vector form. Let us discuss about the vector form of the force between two point charges. When we consider Q1, Q2 are separated through a distance, and the vector notation for the distance of separation can be given as the displacement vector R. If we discuss on force on the charge Q2 due to the charge Q1, the force can be represented as F suffix 1, 2, where 1 indicates the charge which experiences force on charge 2. The displacement vector from charge Q1 to Q2 is given by R1 to 2 vector, and thereby force vector can be given as K times Q1 Q2 by R square multiplied with the direction. This direction says what is the direction of force. The force between two point charges acts along the line joining the two point charges. Or we can say force from Q1 to Q2 will act in the direction of R from 1 to 2. Thereby, the unit vector can be given as AR12, which can be given in the terms of displacement vector as R12 divided by its magnitude. Substituting this into the expression, we can get force as Q1, Q2, and the constant K is 1 by 4 pi epsilon naught. The vector R12 divided by magnitude of R12 cube. You can observe here, when you write only unit vector A, then the denominator has square term. If we write the unit, instead of unit vector, if we write R by magnitude of R, thereby the expression gets R cube in the denominator. We also know the unit of force is Newton. Similar to this force, we can get force on charge Q1 due to charge Q2. In that case, the direction of force will be opposite and it is directed from Q2 to Q1. And the displacement vector is directed from 2 to 1. We are writing the vector as R2 to 1. And the force F21 can be given as K times Q1 Q2 by R square into unit vector. In this case, the unit vector R12 can be given as vector R12 divided by its magnitude. And we should also note here, this R12 and R21 are equal and opposite vectors. Thereby, we can write R12 is negative of R21, and therefore, force also will be F12 is negative of F21. These are equal and opposite forces. Next, if we consider a scenario where more than two charges are present in a region or in a system, what will be the force on these charges? In this case, each and every charge will experience force on every other charge. If we are finding the force on a specific charge, all other charges are going to experience force on that specific charge. Now let us discuss about force on the charge Q1 due to all other charges. We can get the force on Q1 as the vector sum of forces due to all other charges. we can write the displacement vectors from all other charges to Q1 respectively as R21, R31, R41 and Rn1, and thereby their forces, individual forces can be computed, and the net force will be the vector sum of the individual forces. We can mathematically give it as F1 vector is equal to summation of the product of charges divided by 4 pi epsilon naught and the displacement vector magnitude square multiplied with unit vector in that particular direction. If I want to find the force on any random charge, I can indicate it as a general notation Qj, force on Qj, that is Fj vector can be given as summation Qj Qi by 4 pi epsilon Rij magnitude square into unit vector in the direction of Rij, where J is the charge which is experiencing force due to all other charges Qi, where I takes the value 1 to n, where I and j are not equal. So this is the general representation for force on any charge in a system of n number of charges. The next topic of discussion will be electric field intensity. When we discuss about electric field, if a charged particle is present, there will be certain region around the charged particle where its electric force can be felt by another charged particle. That region around the charged particle where its electric force is felt is called electric field, and the measure of that electric field or the measure of the force experienced by a unit positive test charge is called as electric field intensity. If we are about to find the electric field measure of this point charge q at a faraway distance, then we will assume there is a unit positive test charge at that faraway point, and the force experienced by the unit positive test charge due to this charge can be the measure of electric field intensity produced by this charge q. So let us consider a point P where test charge of 1 Coulomb is present, and this is through a displacement of vector r from this charge q. We can first measure the force due to this charge q on the test charge, that is q into qt by 4 pi epsilon r square into unit vector. We can also write in terms of only vector r divided by magnitude. The electric field intensity measure is the force per unit test charge. If I consider force per unit test charge, then the expression for electric field intensity due to this point charge can be obtained, that is q by 4 pi epsilon r square into the direction vector ar. The unit of electric field intensity can be found from this ratio, force per unit charge, which gives the unit as Newton per Coulomb, or the practical unit of measurement of electric field intensity is volt per meter, which will use in the course always. Next scenario is where if there are more than two charges present in a region, and at the point P, if we find the electric field intensity, the electric field intensities produced by all these individual charges will contribute to the net electric field intensity at this point. Thereby, we can find the net electric field intensity at this point P as vector sum of electric field intensities due to all these individual point charges. We can graphically represent in terms of the displacement vectors from these individual point charges to the point P, and the electric field intensities due to individual point charges can be written in terms of this displacement vectors, and the net electric field intensity will be vector sum of the individual electric field intensities. We can write the equation in the form of summation also as given. Thank you.